just giving a Femap webinar on behalf of SIS, and the webinar is an introduction to Femap, and that's basically we'll be covering over the next 30 or 40 minutes. Okay, thank you. Okay, so the agenda that we've outlined is shown on this slide. We'll start off with a brief introduction, just at a fairly high level, about why we should consider using simulation tools, and then we'll review the analysis process very briefly, because that's basically what we're going to be following for the remainder of the webinar. And we're going to be looking in a little more detail at various parts of the simulation process, and seeing how we can really use Femap well, starting off with the CAD data and continuing through to creating an FEA model from that data, setting up an analysis, and finally reviewing the analysis results and some post-processing. Okay, so just very briefly, why should we consider using simulation tools? What are the benefits from using simulation tools? Well, I guess first and foremost is the ability to test designs virtually, rather than having to build physical prototypes and test them, which can be expensive and time-consuming. The ability to build designs in a computer using software like Femap can save a lot of time and money, essentially. Failure analysis, this is the ability to test out designs before they really go out into the field, so that you can verify that they're going to behave as expected, and this does a lot to improve reliability and reduce embarrassing and costly situations like product recalls, which are harmful not only to the company coffers as such, but can also be damaging as far as reputation is concerned, both for the company and the products. Optimizing the design is another good use of simulation, and here we can make sure that the design isn't over-designed, so we can reduce weight. We can use simulation to evaluate different materials, and overall, basically, the idea is to save money with optimization. And the fourth one mentioned on the slide here is trade-off studies. This allows you really just to evaluate different designs, to make modifications to a design and see how it performs. And you can do all this using computer software like Femap. And it really means that the whole try it and see process can be turned around much faster than actually going to physical prototyping. It also allows you to foster innovation with setting up your designs as well. So it saves a lot of time, essentially. Okay, so the process of simulation basically is shown on the slide here, and generally speaking, we start from geometry modeling, which is imported from some CAD system. That's brought into the FE environments like Femap, and we start the pre-processing phase. So that's the creating the finite element model itself. That might require some geometry cleanup, where we apply loads and boundary conditions and material properties, and set up everything that's required for the analysis. The model is then submitted to a solver for analysis, and Femap is bundled with the solver NX Nastran, which is a pretty good solver for stress dynamics, and has some advanced nonlinear capabilities as well. Once the analysis is finished, we bring the results back in, or actually I'll show you another way of accessing results a bit later in the presentation, where we can then actually view the results and see how the design has behaved according to the loads and boundary conditions that have been applied. And we can glean from that whether the design's going to work or if it's not going to work, and we can provide feedback back to the designers to make possible changes if required. So that's really the knowledge transfer back to CAD. That's the slide refers to, and that's one cycle through. Typically, in any kind of design, we'll run through this cycle many times. So it has to be efficient and allow for quick turnaround, basically. So the product we're going to look at today is Femap. This slide here shows an overview of that very briefly. We're going to go into some more detail and various aspect of Femap, but overall, basically Femap is a standalone FEA pre- and post-processor. It works with solvers like NX Nastran. It's a powerful simulation tool. It has a lot of high-performance modeling and analysis setup capabilities, and it's intended really to help people solve their tough engineering problems. One of the principal features of Femap is that it has a very tight integration with Nastran, particularly NX Nastran. So you can actually get a long way to setting up some pretty complex, advanced problems completely within the user interface environment without having to resort to editing decks and the like. Femap has open simulation. We'll talk about what that means in terms of CAD independence and why that's important. Also, it's open simulation in terms of being solver neutral. So it interfaces not only with the Nastrans of the world, but other types of solver. In fact, all the major commercial solvers, and we'll show you that a bit later. It also has acts as a powerful integration platform for third-party extensions. This is really alluding to the application programming interface that Femap has, and a lot of people are really beginning to get into using that, and it's a very, very powerful tool as you can really link Femap with third-party programs and extend the usability of it, essentially. Overall, Femap has a lot of capabilities, but it is a Windows native application, so that essentially makes it easy to use and learn, and it incorporates a lot of the intuitive processes and workflows that we all use in Windows products today. Okay, so let's set off through the simulation process itself. We'll start right at the beginning and look at what we need to do to actually start to create a finite element model. And a good starting point usually is to leverage CAD geometry, the CAD data model itself. So by doing that, we don't need to reinvent the wheel. We don't need to recreate geometry. If we can access the geometry from a CAD system, we can bring that into the FE environment, into the Femap environment, and start to work in it. So the challenges with that, generally speaking, maybe limited CAD support, maybe some tools don't access all of the latest CAD systems, and there may be some data types that are missing. There may be some tools which don't operate in a multi-CAD environment very well. You'll see the quote at the bottom of the slide there from the Aberdeen Group industry analysts. 82% of companies use 3 or more CAD formats. So most people are working in a multi-CAD environment. That's important to be able to transfer data seamlessly and quickly as possible. So the implications, if you come across these problems, you have to resort to other methods of data transfer, which is going to be time-consuming, particularly if you have to build it from scratch. We'll look at what Femap can do in this environment. Femap has access to all of the major CAD systems and data types, and you can reliably import CAD from a wide variety of sources. So you can leverage the existing design model. You don't necessarily have to recreate any geometry. It saves a lot of time. It also works well in a multi-CAD environment, and we have our own CAD systems, of course, Solid Edge, and there's a high degree of interoperability between Solid Edge and Femap that you can benefit from if you use that particular CAD system. Okay, so once we've got the CAD data in, the next set of challenges come through our desire to build a finite element model using the CAD data. So typically challenges may be that the CAD data has too much detail. There may be some fillets and what have you, some detailed detailed modeling information that we just don't need from a CAE point of view. So we need to find that. We need to remove all of that, that extra detail. There may be some bad geometry in the model. The CAD geometry is created to be kind of representative from a visual point of view, and it may contain some kind of sliver surfaces, or there may be gaps in the geometry there which can disrupt the process of creating a finite element model. So the implications then, you waste a lot of time solving and post-processing an overly detailed finite element model. You can waste a lot of time fixing this problematic geometry if it exists. You may even get inaccurate results from badly shaped elements. You might even be able suffer from a loss of modeling data if the tool you're using is overly aggressive in its cleanup methods. You might be wiping out some certain small surfaces which might have loading data associated with it, for example. So if you look at some of the things you can do in Femap, there is this meshing toolbox available. It's an interactive toolbox so that you can actually bring the model in and walk around and work interactively with the model, locating problematic geometry, manipulating it, fixing it, and you can save time and maintain a high degree of accuracy for when you create the FE model a bit later on. And some of the things there, you can find short edges, small surfaces. You can fix things up by combining curves and combining surfaces to make boundary surfaces, so you can eliminate small detail but maintain the overall topology of the model that way. Some other things you can do with the interactive meshing toolbox, you can suppress or remove small features, so that gets rid of a lot of the extra detail that we perhaps don't need. And you can do a lot of things to prepare the geometry for meshing, so you can put mesh seeds along edges or curves. You can maintain accuracy with tools like pads and washers, which allow you to apply a very good mesh around typical stress razors like holes, so you get accurate results where you need them at levels of high stress, changes of stress, high stress gradients. Some other considerations, we may have to depart from the solid model and go into geometry idealization. This is something which Femap excels at. And this may be to deal with some of the challenges that we might be faced when we're trying to create an efficient solution without compromising accuracy. So we have, in some of the solvers like NX-Nastran, there is a choice of solver types. So, for example, you can have a sparse solver, which is the usual one, which can handle a certain model size. But if you want to get into handling much larger models, then you can switch to using the iterative solver. And you can see from the graph on the right there that you can certainly handle much larger model sizes with that iterative solver. However, that solver can only be used for static analysis. So if you want to get in and use some more advanced types of analysis like dynamics, or maybe go into some nonlinear, then we have to resort back to the standard sparse solver again, which means model size becomes one of the foremost things to consider. And we can have a lot of tools that can get into geometry idealization, which can help us reduce model size without compromising accuracy. And that's what we're going to be looking at over the next couple of slides. So we're talking about things like mid-plane extraction. If you have thin-walled models, thin-walled solids, you can see that if you try and mesh those with solid elements, you're going to quickly create huge models. A much more efficient approach, and actually potentially just as accurate or even more accurate, would be to extract the mid-planes from the thin-walled solids and then mesh those with two-dimensional elements like shells. And you can see a model comparison here, fairly basic kind of model actually. The solid model is 53,000 nodes and the shell reduces down to 11,000, so a much faster model to run, particularly when you get into some more advanced types of analysis. So mid-plane extraction is very robust in Femap. You can take that even further and start using beams to represent certain topologies, long, slender types of topologies, for example, and these are one-dimensional elements, of course, so that's even more efficient from the solution point of view. And Femap has a lot of capabilities that help visualize beams, because the 1D elements, and a lot of systems will just draw them as lines, but you can actually represent them as a 3D shape, which helps orientate them, make sure that offsets are correctly positioned, that kind of thing. So there's a lot of capabilities like that in Femap. Okay, so moving on to actually creating the mesh itself. The objective really is to create an accurate and efficient finite element model. And some of the challenges you might find at this stage, we're really looking at creating a mesh with well-shaped elements, because there's an accuracy consideration here. Distorted elements will yield less accurate results. So we want to make sure that we don't have any of those, particularly in the areas of interest. Some badly shaped elements, Nastran will even stop the solution if it comes across elements which are just too badly shaped. So we don't want that to happen. We want to, actually get a solution by making sure that the elements are, well shaped. Debugging this can be time-consuming and quite difficult locating, and fixing these badly shaped elements. So really, the efficiency of the solution is a major consideration here. We want to minimize the model size, maintain the desired level of accuracy, and save a lot of time in the solution process. So one example here, if we look at a rectangular plate with a hole, we have different sets of mesh density here, and you can see how, with a very sparse mesh, the accuracy is sort of compromised. And as we go to finer meshes, the solution approaches the closed-loop solution, which you can see in the graph on the right. So really what we want to do is to get an accurate solution, but minimize the number of elements to make sure that the analysis is as fast as it can be. So we can do that by actually changing the mesh density and making sure that we have a fine mesh in the area where it's needed, where the area that that there are stress raises, particularly around the hole in this case, where stress gradients will be changing pretty quickly. So by refining the mesh in those areas and making the mesh coarse away from the areas of interest, we can get a good compromise. We get accurate results and a small model, which means it'll work efficiently. So that's a simple example of what we're trying to achieve here. So some of the challenges then, really controlling the mesh, controlling the size of the mesh, refining it where we need to refine it, and having a coarse mesh away from those areas of interest is important. Meshing workflow is consideration, and I'll talk about that in the next slide. And model checking too, that's important, to be able to check the model before we set it off for analysis. Again, back to my comment, making sure that the elements are good enough so that Nastran is not going to stop in its tracks and complain about element shapes and so on. Okay, so one of the things about meshing in Femap, we have the meshing toolbox, which is an interactive toolbox, as I mentioned earlier. Typically, the meshing process has a serial workflow. You'll edit geometry, you'll set the meshing parameters, you push the button to mesh, it creates the mesh, and you can evaluate it. You look at the mesh and see if it's good enough. And if it isn't, then you have to delete it and you go right back to the beginning again. With Femap, this whole process is interactive. So you can mesh the geometry, then you can edit and remesh. You can have it sort of remesh automatically every time you do something, or if you want to do several things at once, you can set it to that you perform several actions and then hit a remesh. It just makes the whole process much easier. You can see what you're getting as you're going along, and it's a completely interactive workflow, basically, which is a much more efficient way of working. So we have a look at the meshing toolbox here. This is basically the everything that you can do in the meshing toolbox. You can go from suppressing features to completely removing them from the model. There's feature editing, the geometry editing, the combined curves and surfaces that we saw a couple of slides ago. You have complete control over mesh sizing. You can control mesh surfaces. Mesh locate can help you find areas in the mesh that you might want to change. And finally, the last one there is mesh quality, and you get a red-green plot of the mesh, and it shows you, according to various different criteria, how your mesh will stack up, basically, as far as quality is concerned. Other things that you can do in the interactive meshing toolbox, you can update mesh size on curves, and you can also set to have mapped meshing, and the two images on the left show you what I mean by that. So you can actually map so that you get the same number of elements from one edge right through the surface to the opposite edge, and it just makes for a much nicer looking mesh with better shaped elements. Mesh quality, I mentioned this is the red-green plot here that you can get, and you can set your criteria, to be one of several that are available. And I think this slide shows Jacobian. Here's the measuring criteria, and you can get, again, it's interactive. You can get a plot of what the elements look like, whether they pass or fail, based on the criteria that you selected. There are also other checking things that you can do. Checking for coincident nodes. If you have any coincident nodes in the model, that means you have two elements which are adjacent but they're connecting to different nodes. That means basically you have a split in the model, so it's not continuous. That might not be desirable. That will introduce errors. Same with coincident elements. You might have double elements, difficult to see, but they may exist in the model. Femap has ways of checking those. You have free edges and faces that can highlight some of these things. You can check your loads and constraints. You can do things like sum forces. You have mass properties that you can check the weight of the model, make sure that's correct, and various things you can do before you set the analysis off. One last thing you can do here is actually interactively move a node around. So you can actually go down and pick a node and move it and have it adhere to its underlying geometry, so you're not pulling it out of plane or anything. And you can move it around, and in this particular case we get to a position where all the elements go from red to green. So that satisfies our element checking criteria. So that's pretty neat too. Okay, next thing, once we've got the mesh, the model meshed and the finite element model is there, we might want to think about some boundary conditions, setting up some boundary conditions. This is perhaps one of the most challenging aspects of finite element analysis, to make sure that we create accurate boundary conditions that represent real world behavior, essentially. And the more we get into more advanced types of analysis, such as dynamics, then the more complex boundary conditions setup can become. There are situations where we might want to take the results of one analysis and apply it as a boundary condition in another. I think we've got an example on the next slide that shows that. One of the capabilities that Femap, before I get to that, there's an example of how boundary conditions can be pretty important and lead to bad answers, essentially, if we're not sort of vigilant about how we're setting up. In this simple link and pin example, in the model in the top, we've opted to completely glue the pin to the link, so that we have a transfer of loading all the way around the circumference of the pin. That might not actually be what we wish to represent. In the bottom model here, we've set it up so that it's a linear contact, so it's the link has the ability to pull away from the pin without load transfer. So it's really only a bearing force on the left-hand side of the pin that's transferring load. And you can see this simple example can give you completely different answers. So it's something to be vigilant about. Very easy to get the wrong answers if you're not careful about boundary condition setup. Okay, so some of the capabilities in Femap that really can make this a lot simpler to set up, particularly for more advanced types of boundary condition, are data surfaces. And we have a data surface editor which allows setup of complex spatial load definitions. So you can 1, 2, or 3D spatial variations, and you get an output map data surface as well. So you can do things like the images on the right there. If you have a kind of a thermal mapping that you want to apply to a structure, you can set that up very easily in Femap. moving those things around and aligning them as you wish. You can also set up other complex load systems. For example, the images along the bottom left go from a fluid, essentially a fluid model, which exerts pressure loading on a structure, and that can be mapped to a structural model for a subsequent analysis, that kind of thing. We can get into some nonlinear constraints, and that's the Nastran C-bush, essentially, that we're talking about here. And this is a nonlinear and frequency-dependent generalized spring and damper element. And you can do a lot of wonderful things with this kind of element to get into more advanced types of boundary condition definition. And also from the point of view of components which will fit together, Femap offers a variety of robust assembly connection methods, and some of them are shown on the slide here. So, for example, the top right image is really a surface connection. We have a turbine blade model there, basically, and we're connecting a hexa meshed blade to a tetra meshed base. And as long as the two components have, they share a same plane of connection, then you can do this. And the results are actually very good. It's a good way of connecting dissimilar meshes. You have other things like fastener elements. There's bolted connections as well, and surface contact. Three other images shown on the slide here. So many and various different ways of connecting together assemblies of components, which is more and more required these days. Okay, so once we've got the model set up, everything's set up, we now want to submit it to run for an analysis, and we need to create the input file and send it over to a solver for the number crunching stage of the process. So challenges here may be, you need to access more than one type of solver. If you've got more than one type of physics to consider, for example, you might want to consider as a structural analysis. Maybe you want to also drop test the design to see if it will withstand that kind of analysis. So you may need to access more than one kind of solver. Access to advanced analysis setup, too, might be a challenge. As I mentioned before, what you want to avoid having to do is to drop out of the pre-processor user interface and have to start typing in entities for the analysis by hand. That requires you to take on another kind of level of information about the language of the solver itself, which, as long as you can stay within the user interface, you perhaps don't need to do. So that's another challenge, perhaps. So let's see what Femap can do to help you with this aspect of it. Well, Femap accesses all the major commercial solvers for analysis, and you can see there's three flavors of Nastran. TMG are advanced heat transfer and flow solvers that are also bundled with Femap. Femap has a lot of ability to interact with LS-DYNA and other solvers, Cinder, Adena, which is a advanced nonlinear solver, actually, that's also bundled with Femap, as well as other commercial solvers like ANSYS and Abacus. So you can access all of those solvers with Femap, and there's a very high level of integration. As well as that, you may want to have the ability to scale your simulation. So you might want to go beyond simple statics and normal modes, perhaps into a full dynamic response. Maybe even design optimization. You may have a requirement to get into some more advanced nonlinear. You can do that with Femap. Femap with NX Nastran has a lot of capabilities, and you can go in and use the thermal and flow solvers as well if that's also a requirement. So a lot of scalability here from the point of view. Okay, so once you've got the analysis solved, the next challenge really is to take a look at the results data, and the objective here is to be able to efficiently review all of the data. Now, you can imagine that with increasingly large models, the amount of data that's actually produced by the solver is also going to be increasing as well. So the quantity of results data can be a challenge. Once you get into more advanced types of analysis, again, the amount of data will increase. So rather than a single solution for a static analysis, for example, once you get into a transient response, you get a single solution for every single time step. So you can see that's going to very quickly create a vast amount of results data. Similarly for nonlinear, maybe load steps in that case, or frequency steps if you get into a frequency response. So a lot of data to get through. There's going to be some time considerations to access all this results data. There's going to be some hardware usage as well, memory in terms of processing all this data. And you're going to have to be able to deal with large and unwieldy results databases too. So let's see where Femap can help out. And one of the things that we added to a more recent release of Femap was the ability to get around the need to import all the results data into the Femap database. What we can now do is actually attach to an external results data, which makes access to results much faster. And also, interacting with results is a lot faster as well. So much more flexible way of accessing results data for a start. Other things when we're looking at results data, we need to review and comprehend the results data to get an appreciation of how the design is performed according to the loads and boundary conditions that have been applied. So we need to do that efficiently, and we need to communicate those results efficiently as well. So the challenge is typically speed, comprehension, and communication, and that's what we really need to consider when we're looking at results processing. So Femap has a great wealth of capabilities here to help you investigate the results once the analysis is finished, and you can get a lot of ways of presenting the results data or viewing the results data with deformed shapes, full contour control. You can animate the results. Free body displays are important. I'll show you those in a minute. Maybe to view results inside a solid model, you need a dynamic cutting plane or an ISO surface. You have full output control, flexible result selection, things like grid point force balances give you an appreciation of how the model, how the results run through the model, which is important in some analyses. Essentially, with a lot of analyses, people prefer to look at force data rather than stress data. It's a more stable way of viewing analysis results, essentially. So Femap offers the results, the post-processing toolbox to help you access and review all of this results data. And this is a piece of the user interface which really consolidates a lot of the access to a lot of the post-processing functionality in Femap. So it allows you to quickly set up and change all these post-processing options. And you can do it, again, you can do it interactively, which is a much better way of working. Some things will be pretty difficult to get in and view. You can imagine things like line elements or beam elements. How do you get in and actually view those results? Femap has a lot of capabilities there to help with that. You can view results across beam cross sections. You can see shear flows and stress distributions. You have full control of forces used to create those those output contours, and you can calculate some others as well on the fly. So you're not completely reliant upon what the solver provides. There are also beam diagrams, which are a good way of looking at bending and shear force in beam models. So there's a way of getting to those types of results. And generally speaking, Femap offers you full control over what you want to look at, full control over the results viewing as well after the analysis. It offers things like with plate results, and the model on the bottom left is actually a plate model shown in 3 dimensions, so you can actually see stresses through the thickness there as well. And there's a complete XY plotting or charting capability in Femap as well, which has recently been updated, and that's a very good way of viewing results as well. I mentioned earlier the free body diagram capability. So you can take a chunk of structure and view the free body diagram of that structure. Also, another aspect of using this is to get interface loads between two interacting pieces of structure. So there's a rib against a fuselage skin shown on the right-hand side there, for example. And there's also a data table that Femap has as well, and this is a very powerful tool actually to help you assimilate all the results data. It helps you knock down just what you want to view. There are all kinds of highlighting tools as well, which show where results, particular results, appear in the model. So it's again a very good interactive, dynamic way of sorting, filtering, and evaluating the results. It also has some ranking tools that allow you to compare data from different output sets, or indeed different models. And you can interact with the clipboard as well. So you can get all this data, copy it to the clipboard, and copy it straight into something like Excel, and that's a two-way capability as well. So very powerful capability, the data table. Okay, well that sort of brings me around to the concluding slides then. Once again, just we've seen some certain aspects of the use of Femap, some of the things that it really excels at, and some of the more challenging aspects of performing simulation that Femap can help out with. But we haven't seen everything in Femap, obviously. So just to really summarize, Femap again, it's an easy-to-use interactive user interface. This allows increased productivity, reduced learning curve, and training overhead. It has comprehensive modeling functionality that really solves complex engineering problems. That's really what it's designed to do. It allows the user really to get in and get down to the nitty-gritty of finite element analysis and finite element modeling. It is a high-quality solution, which ensures as much as it can that results are going to be accurate. It's CAD independent. It's an open simulation tool. It's CAD independent, solver independent, as we've seen in the slides. And finally, I mentioned this before, the application programming interface, the API, really allows it to become a very powerful integration platform. You can integrate Femap with any kind of third-party kind of tool, and we've seen people do that actually. They've third-party. Some of our technology partners, for example, have integrated fatigue solution on top of Femap, which works pretty well. Okay, so to find out more, there is a 45-day trial available that you can get to online. So you can try it out, try Femap out for yourself. It comes with dynamic response, and it's completely unlimited except for time. Unlimited as far as modeling is concerned, but limited to 45 days length. So that's a good way of evaluating the product. Another thing I want to advertise, coming up in May in Atlanta is the Femap Symposium. That's a pretty good event to go and attend if you want to find out more about Femap, and an opportunity to interact with other Femap users, as well as some of the developers that develop Femap too. Okay, so with that I'll conclude my presentation, and I'll return it back to you, Alexandra, and open up for questions.